Hello, this is my presentation on the Memristor. So introduction, the Memristor is a programmable resistor that can make various resistor functions and has memory states that it can tell what state it was in even if the power is disconnected. This device was theorized in 1971, but it took till 2008 for Stanley Williams to actually make the first fabrication of a Memristor. And to the right, you can see on the top that that is an actual what Memristor chip looks like. While the bottom, this is what the circuit diagram of a short circuit representation of a Memristor would look like. So Stanley Williams' first design, he used what was called a crossbar design. This was an array that we can use to store a lot of information. But for a Memristor, it's basically behaving like a switch. They want to change from the off or the on from the off resistance to the on resistance. To do this, he needed to change physical properties. So between the green bar and the yellow bar, there is a semiconductor in between it. And Stanley found that if you could change the one dimension of the semiconductor by 2 to 3 nanometers, it will boost the resistance up by a factor of 1,000. So using that, this was Stanley's first design. So over here is it in a normal condition. So we have two, or over on the left, sorry. We have 2 layers of platinum on the top and the bottom. But then we have a TiO2 on the bottom, this green one. And then we have TiO2 oxygen deficient. So oxygen deficient makes the vacancies positively charged, while TiO2 is not. So you kind of think of it as the top is being doped while the bottom's being undoped. So using that, or when you apply a positive voltage across the 2 platinum terminals, you get what's more in the middle. The positive ions push down on our vacancies of our TiO2, increasing the layer or increasing the overall length. While if you apply a negative voltage, it actually pulls it back up and then decreasing the length. So from NanoHub, these are what I should expect from my graphs. So since a memristor is behaving similar to a resistor, our most important graph is the voltage versus current. This is basically going to show us what our resistance looks like and how it varies. Another thing we need to know before we look at our first graph is that a memristor is a nonlinear device, because as you put a voltage across it, the TiO2 is also moving, which will be increasing the resistance. Likewise, if you put a negative voltage on it, it moves it backwards. So we are going to get this nonlinearity property of it. And lastly, because the memristor is a resistor at 0 volts, we should expect the device to have 0 amps, because this should not store any energy. Okay, so our first graph is I had various inputs I can change on NanoHub. I wanted to see how the angular speed affected the output resistance of the memristor. So as we can see on our graph here, the 5 is this green graph, and you can see there's huge varies in the resistance. But as we start increasing the frequency more and more to the blue 15 rads per second, we actually get something that's pretty close to a linear function. So higher the frequency, we can conclude gives us a more or less vary in our resistance. The other result I wanted to change is I wanted to change the ratio between the max resistance to the min resistance. So the ratio between off and on, off being the max and on being the min. So as we keep changing the resistance, you can see that our graph is getting pushed more and more and more to the right. Because the voltage is the input, this means our resistance is actually increasing as the ratio gets bigger and bigger and bigger, which makes sense because our overall ratio is increasing. So we should expect something like that. And the last thing I really wanted to look at was the changing the carrier mobility of our semiconductor. When we change it, you can see that it's getting pushed more and more to the right, making so as the carrier mobility increases, there becomes less deviation, there becomes less resistance, which this makes sense because we're increasing the ability to a for or the increasing the carrier mobility increases the willingness for electron to move. Lastly, these are my conclusions. The Memristor is a very fast-growing field because of their ability to store ample amount of information in a small amount of area while being cost-efficient. HP actually did a study, or they were working on in their labs, that if they put multiple Memristors in layers, they can actually create a storage device that can store 128 terabits per centimeter squared, which is insane. Like, this will get rid of all the hard drives. You can have cameras being stored on nothing, or a little tiny chip for year, or cameras can use pictures for years and years and years of this little chip. Memristor is predicted to be the next generation for most of these integrated circuits, replacing what has been mainly used by transistors. And lastly, here's my works cited page, all the places I got all my information, and that should be it. Yeah. I want to thank you for giving me the opportunity to research the Memristor. I found it very interesting, and yeah, thank you.